Yeah, good. Okay, morning. Brian is my name. Okay, I go straight to icebreaker because to how to say, to create a very conducive environment for us to continue to learn. Okay, I would like to ask, do you, any one of you know who's the inventor or father of air conditioner? I give you 3 options to guess. Yes. See who can guess it correctly.
B. Willis
It's okay, yeah. All right, anyone? Huh? B, yeah. So B, yeah. Very good. Okay. Yeah. Carrier. Everybody know, right? He actually invented the aircon, a modern aircon using refrigeration systems in 1900s, year 1900s. Okay. That means almost 124 years already. Okay. Second question, guess my age.
20.
Huh? Okay. Just now he guessed my 60, you know. So hurtful. So hurtful. Huh? Okay. Okay, number 2. Which business sector do you think the modern air conditioning are first time using it? Which sector? Printing, restaurant, fabric. The first timer of using the modern air conditioner. Restaurant. How about others? Factory, yeah. Factory. Okay. Yes, factory. You know why? Fabric factory actually they are very sensitive to humidity. Okay. So that was the reason actually the first air conditioning to use to control the humidity level. Okay. So okay. Today's topic, yeah, I would like to share with you all the fundamental principles of air conditioning today for you all, and what are the different types of system that available to you for you to adopt it for your future designs and comparative advantage among them. Okay. Yeah, now time to know more about me. Okay, so my name is Brian Kaur. I'm the MD of Chemwise. Okay, I started my career. Oh, yeah, can you see? Cannot see, huh? Can you see? Okay. I started my career in Denham Bush, okay, in 1995 for 14 years. Then after that I left and set up this Smartech company called Smartech. I was the CEO from 2019 to 2011. Okay, so after that I left the company and set up this Chemwise in 2011. Okay, and then I was the past president of Malaysian Aircon Association for 2 terms. President, no? Okay. So I was regular speakers in many seminars in many associations, and I have what I call managed many projects in the past. Huge projects, especially district cooling using ice thermal storage. Okay, this is a bit about myself. The course objective to provide participants the basic knowledge of air conditioning and build up some fundamental skills to differentiate and or identify different types of systems. Okay, they're available to you when you do the selections for designing aircon system. By the end of these trainings, you'll be able to apprehend the fundamental knowledge of air conditioning and possess basic skill to continue further develop your competency in design and real site applications. And you'll be able to differentiate and identify different types of systems and choose the right options for optimum design. First, let's learn how to identify where are the sources of heat inside the aircon space. Okay, so when you want to actually what I call cool down the air, of course, inside a space like this room, for example, so you must be able to identify where are the heat sources coming from. Okay, one of the very first component is the solar heat, the sun. Okay, the sun actually is coming into the space through what? Through window, through wall, and through roof. Okay, so when the sun actually coming through the windows, there are two very fundamental ways. One, actually the heat directly, you can see, you can feel that it's directly radiating into the room, and you feel the heat of the bodies immediately. Okay, but that's what you perceive. But the air conditioning load that created by radiations is not instantaneous. Okay, the air conditioning load actually generated from the solar gain through radiations is being translated into the real air conditioning load after it is being absorbed by the structure, by the wall, by the floor, by the ceilings. After it's absorbed, and then it's stored up to the maximum storage already, and then it slowly and gradually being convected out from this structure, and it becomes the actual cooling load to your air conditioning equipment. There's a lot of people actually they was not aware. They always misunderstood how actually the way of radiation load being calculated and translated into your aircon equipment load. And you can, from there you can immediately, feel that radiation load is the most difficult part of the air conditioner to handle. For example, if you stand actually just beside the window like this, it's very hard for your aircon actually to handle the heat that you feel from the sun. But of course, that if you can have an aircon directly blow the air onto your body, it's okay. But this is not the way the aircon is supposed to be designed. You have to, the real purpose, the real objective of the aircon is to make sure that the air is slowly, evenly distributed over the entire space that you want to provide air conditioning. Correct or not? So if let's say if the air is only directly blow into your bodies, then other people, they cannot enjoy the aircon. So that's why I say the load radiated, the heat radiated from the sun through the window glass is very hard to handle. This is the part that actually we have to be able to know the underlying concept and know how to translate into the actual cooling load. Okay? And then another way of the heat transfer into the building actually is through the conduction. Just now is radiation conduction. That means conduction actually is driven by the temperature difference between the outdoor air and the indoor air. So when there is a temperature difference, the heat will start conducting through actually the glass, the solid glass, and come into the room. There are two ways, correct? Okay. So these two actually combined together become actually the solar load through the window. So this is a very first component that we need to, if we do the heat load calculations, this first component we need to identify and we need to establish. And then after that, of course, through the wall. Of course, through the wall is definitely actually through conduction. And the conduction actually is not instantaneous because the heat will transfer slowly, layer by layer. And it depends on the storage capacity of your wall. Okay, that will affect the rate of transmissions. Okay. It's like the thicker actually the wall, or the bigger weight of storage of your buildings will actually will affect how much conversions of the solar radiation into your actual load. Of course, the bigger storage, the less conversion. So that's why in the designing actually the structure of the buildings, the architect are also affecting the cooling load. And that also will affect what? At the end, ultimately, because your aircon need electricity energy. So the architect also need to strike a balance between the structure cost and the long-term energy that you need to pay by the owners for the electric bill running the aircon, correct? So that are the many factors that we design. A lot of people nowadays they use rule of thumb, 60 PTO, 50 vehicles, they have all bypassed all these important underlying factors. Another load, your human body. Your human body actually is one of the very substantial component of heat load into the aircon space. Okay, of course, your body generates two types of heat. One is sensible heat. Sensible heat is the heat that you can use the thermometer, you can see there's the temperature rise. Sensible, you can sense it. Okay, another heat is latent heat. What is latent heat? Latent heat is actually the type of heat that is caused by the moisture content inside the air. See the, okay, this vapor coming out from your body, creating a latent load. This latent load actually will affect the humidity or the relative humidity level inside the space. Why I want to touch on this because that the ultimate objective of designing aircon is that there are two important, not limited to, but two important criteria. One is the dry bulb temperature. You need to achieve a temperature that your body feel comfortable. Typically 22 to 24 degrees C. Okay, dry bulb, we call it dry bulb. A dry bulb temperature is the temperature that you can use a thermometer. Dry, whatever register in the thermometer is the dry bulb temperature. Okay? But there is another temperature called wet bulb temperature. This wet bulb temperature is the indicator of how humid or how much moisture content inside the air. So how to actually use thermometer to measure this wet bulb temperature? In fact, actually, I want to collect back the sink psychrometer. Okay, a thermometer where the red bulb is covered by a wet cloth. Wet cloth, and you swing it fast enough. Okay, then whatever temperature registered on the thermometer is called a wet bulb temperature, and it must be lower than the dry bulb temperature. Okay. Why? Because what I call the moisture content inside the air normally is not 100%. Okay, whatever moisture content or humidity contents is less than 100%. Those evaporations, whatever evaporations from the wet clothes actually will cause the bulb, the surrounding temperatures will drop. That drop actually is an indication only. It's not exactly the measurement. It's an indication how wet, how much moisture inside the air. I think that is important for Wong to understand it. Okay. So meaning that actually at the end of the day, no matter what system, how hard you design the aircon systems, you want to achieve two, but not limited to two very important criteria: dry bulb temperature, cold enough, and then also dry enough. Cannot be so wet and cannot be so dry. Humidity level where you feel comfortable. A human normally is, you guess what is the percentage of humidity level that you think is comfortable for human? Good. Yes. It's about 55%. That means that in this space, it can actually accommodate, let's say, for example, 100 number of molecule of moistures, but now inside here only 55 molecule is existing inside the air. We call 55%. That's how we actually determine the relative humidity. Okay, and then computer, all this machine here also generate heat. So these are the heat that actually is being generated. That the air coming here actually need to absorb slowly before it go back again and then recycle this. Okay, and like say this machine, for example. Okay, what else? Lighting. Okay, it's one of the component of heat that you need to take care. Okay, So, and then the next door is the warehouse, right? It's not aircon space. The temperature next door actually is higher than the aircon space here. So when there is a temperature difference, there will be heat transfer. So they call it partition heat. Partition heat. I mean, this is a partition where the temperature next door transfer the heat due to the temperature difference. Okay. Now actually the upstairs level 1 is not operating aircon, so it's higher temperature. The heat also will transfer from upstairs through the ceiling. So another source of heat. Understand? So of course, when these are one of the units where you see deliver the air inside the building. Of course, inside here there is a cooling coil. So this basic system, you cannot see that when during the delivery cooling medium through the entire process, there are some losses. These losses also will generate heat for the aircon. That's why you see this component, later I will explain to you, through the piping, through the pump, through the fan, all the blower, motor running also generate heat. So these are all the also one of the component of heat that the aircon need to take care. Okay. So of course through this slides, you can see the overview of all the various components of heat that is being generated inside the space through and also through delivering the cooling mediums into the aircon space also. This slide is showing that just a very simplified overview of air conditioning systems I categorize it into 3 main categories. One, direct expansion system, chill water system, and associated system. Chill water system is a direct expansion system is very straightforward with what you see now, outdoor, indoor, inside the copper tube is circulating with a cooling medium of refrigerant. Okay, why you call direct expansions? Because when the refrigerant is coming into the cooling coil here, it directly absorbs the heat from the air. So it's called direct expansion. So whatever system where inside the space, the cooling coil is using refrigerant directly absorbing the heat from the air, we categorize it as direct expansions. Okay. Chill water system is no more direct refrigerant cooling the air. Okay, we have to isolate by using a centralized chiller system, where the chiller actually is stored in one of the central locations, and this chiller is running refrigerant within the machine itself, but at the same time producing chill water through the evaporator. And the chill water that is being generated is circulating by the pump through the chill water pipe and supplied into the coil here, where the chill water is cooling the air. We call chill water system. Of course, I'm going to show you some of the sample design. Okay, and for both type of systems, either is a direct expansion using refrigerant to cool the air or chill water to cool the air. It can be further subdivided into smaller category. It's either air cool, water cool, or air cool, water cool. So air cool, either direct expansion or chill water system, is using air to extract the heat from the condenser. So whenever a condenser, outdoor condenser, is using air to extract the heat from the condenser, we call air cool. Like what we are using outside here, actually is air cool system, because you can see the air is extracting the heat from the condenser. Water cool. Water cool is a system where we need use cooling tower. Where the water is circulating, is pumping into injecting into the condenser of the chiller to extract the heat, and is the heated condenser water is being circulated into the cooling tower and dissipate the heat to the outside air. So whatever system that using water to extract the heat from the condenser of the refrigeration system is called water cool. So chill water also same thing. It can be either air cool, water cool. Okay, there are some associated components for this both I'm going to share with you in the following slides. Okay. Oh, yeah. So this is a very basic refrigerant cycle, okay, where you have 4 components. You have compressor, you have condenser, you have TXV, you have evaporator coil. Okay, so all the aircon systems, no matter how complicated they are, either chillers, they all derived by this basic refrigerant cycle. Okay. So now, looking at the existing system in the aircon space here, or this room here, this is a evaporator coil inside this cassette unit. There's a cooling coil here, okay, and a blower. So when you start using the remote control to activate the system, to start the system, okay, the first thing, the system, the component that will run actually, of course, is the blower. The blower runs the blower. So the reason actually, of course, to suck the air from the space here, and then go inside the cassette unit, and then running through the evaporator coil. Okay. So at the same time, when you start this one, okay, there is a control wire also to tell the compressor there to start running. Okay. So when you do this, the refrigerant inside the evaporator, when the air actually running through the cooling coils, the room air, which is relatively warmer, they transfer the heat to the refrigerant inside the evaporator, and the refrigerant directly expand. They call it direct expansion system. Okay, and then when the compressor start running, and then it will suck into through the piping, suck through the outdoor compressor there, and then the compressor compress and pump higher pressure into the condenser. When you raise the pressures of the refrigerants, the temperatures will be higher than the outdoor temperature, and then it will reject the heat when the condenser fan blowing the air through the condenser coil. So, and then the refrigerant, gas refrigerant actually is condensed, and at I call it at lower temperature, but you need to go through a direct expansion valve to reduce the pressure before it go into the evaporator coil. So of course the whole purpose is actually to extract, the whole process is to extract the heat from a room where the temperature is lower, relatively lower, to the outdoor air where the temperature is higher. Try to imagine the temperature is transferred, the heat is transferred from the indoor where the temperature is lower to the outdoor air where the temperature is higher. This actually is against the basic principle of thermodynamics. Okay. When you need to transfer the heat from the low temperature to high temperature, so you need to do some work. That work actually is now being carried out by the compression, this compressor. Okay, the compressor actually is doing the work where it's raised the pressure and temperature into the condenser where it's higher than the outdoor temperature. So when you do this work, you need to consume a lot of power. The work being carried out by these compressions need a lot of power. That power actually comes from TMB. You know, for air cool this one, for every 1 ton of cooling actually that you need to provide cooling here, it consumes 1.2 kilowatt or 1.4 kilowatt. It's very power consuming, you know. So of course that come back to our operation here. And you can see that the view, then you know already. Yeah, this is showing one of the sample design, where you have an indoor, outdoor, connecting with all the copper piping, right? Of course, VRV actually is supplying actually all the multiple indoor. Okay, coming back actually. Okay, coming back to this one. Okay, I want to demonstrate one by using this prop actually to tell you that how to actually control the humidity level inside the room here. Okay. With this actually glass of ice, can you see actually what is happening on the surface of the glass or not? Condensation? Okay. Why? Let's say you try to imagine, you take from your fridge a can of Coke, taking out from there. After maybe few minutes, you can see actually you can see there are some water droplets, okay, on the surface of the can. Did you realize that? This same here, you can see that actually you can touch. The surface here is cold, and then the water droplets start forming on the surface, called condensation. Why? Okay.
Inside is colder than outside.
Technically, actually, because the surface of the glass is lower. The temperature of the glass is lower than the dew point, the air dew point. Air dew point. The dew point means that let's say dew point. Even though let's say you go to sometimes the next time you go for morning walk, you can see some of the glasses, the leaf. Also, there are some water droplets forming. Also, right? Okay. It's because the surface temperatures, the surface of the leaf there is colder, where the dew point of the air. The dew point of the air is the temperature where whenever you have a surface lower than this temperature, the water inside the air will start coming out. That means there are moisture inside the air that is floating inside the air. You cannot see now, right? Okay, because they're in the form of moisture, you cannot see. But in order for them to come out into a physical, visible structure, okay, you need to provide a surface lower than the temperature they need to condense. That means to convert from the moisture in the vapor form into the liquid. Okay, so dew point is a temperature where the moisture in the vapor form start converting into liquid. So whenever you have a surface temperatures lower than the dew points, then the water drops from it. Why I want to demonstrate this process by using this prop is that because one of the very important process of aircon is that the coolness of the surface of the cooling coils have to be lower than the air dew point inside the air in order to extract the moisture, so that the humidity level here is controlled well up to the level that you feel comfortable. Oh, okay. Is it very technical? Okay. Okay, just a very simple process where you say, okay, this is one of the air-cooled split package. This is the AHU. This air handling units, like what is showing here. You have a blower, you have a evaporator coil inside, okay, and then of course that you have a motor inside. You have a motor inside, okay. Every time when we start the system, we start this one first, right? Okay. Then the air is circulating inside the room. Okay. And then the next thing, compressor. When they start compressor, of course, the refrigerant inside the pipe system will start circulating. Of course, the next thing actually is condenser fan. Okay. So meaning that the air inside the room will transfer the heat into the evaporator coil, into the refrigerant, and start into the compressor in the outdoor, compress, and then after that reject the heat through the condenser coil to the outside air, and then come back here, become the lower temperature, but this lower temperature is not sufficient to cool the outside air, but it needs to go through an expansion valve. The expansion actually will reduce the pressure drop. By reducing pressure drop, the temperature will bring down lower to the room temperature, the room air, so that actually that it will continue to absorb the heat from the room air again. So this process actually will illustrate. Can I ask actually, it's a bit technical. So where is the on-coil temperature? What is the on-coil temperature? Yeah. When you select aircon equipments in the supply catalogs, supposedly they are what I call very many technical data. You need to actually use that actually to select equipment. One of it is the air on coil temperature through the cooling coil. So what are the likely air on coil temperature that from this one that you can see? So what is the likely air on coil temperature? Yes, that is what? Room temperature, but this is, I know, dry bulb, right? Okay. So if I'm going to tell you that, now the room RH is 55%, for example. Okay. So what will be the likely wet bulb temperature that you need to determine? Now, if let's say you say that, of course, that without the outside air, the dry bulb temperature is 75 degree F. I agree with you. That is the on-coil temperature. That means that is the temperature that you enter the coil, and this is dry bulb. But given that the relative humidity inside the space now, okay, without all the outside air, is 55% RH. So what is the likely wet bulb temperature? about 62, 63 62 point. If I'm not mistaken, it's 63.7. 63.7 degree F. So you go to the psychrometry chart. Dry bulb 75 degree F. Okay, vertically go up here. RH, here's a 55%, right? Okay, so you draw a diagonally line. This is wet bulb. Okay, so this wet bulb, based on my experience later, if you 75, wet bulb 63.7 degree F. Okay. Okay, and then another question is, what is the air entering the condenser temperature? Yes. Huh? Okay, yeah. It's 95. Yes, 95. Okay. There are many terminology used. Okay. you can say this is outdoor air temperature. Some supplier, they say, okay, what is the outdoor air temperature for the condenser? But some actually consultant, they will specify in different way. They say, what I want the air entering condenser coil temperature is 95. Okay, because this temperature is actually determining affecting the capacity and also the power consumption. Of course, our condenser air is more affecting actually the power consumption. Okay, capacity is not very substantial, but this air entering evaporative temperatures is affecting a lot. There was one, especially nowadays, all the echo split system that supplier is so-called rated standard conditions is not this, no. It's actually 80 degree F dry bulb and 67 degree F wet bulb. You look at the catalog, all their standard rated conditions they call it on coil temperature. Okay, but meaning that if let's say these temperatures, you can see why they actually air-on coils is higher than the room design temperature. Normally room design temperature is about 35, which is 74. Why actually they want to rate their air-on coil higher at 80? If you calculate the mixture formulas, these temperatures have incorporated fresh air. About, if I'm not mistaken, 20%. That means they already rated these on-coil temperatures by including pre-including outside of 10% mixed with the return air. Okay, but you know all these designs does not come with fresh air, for example. So this rating, please bear in mind, using higher on-coil temperatures is giving a higher rated capacity in the catalog. So whatever capacity that you select from the catalog, you have to be careful. That means the capacity might have been overrated more than 10%, maybe 10 to 15% overrated. So when you design any systems, if you know that you are not actually so-called using this on-coil, you better mark up the capacity. That's why a lot of consultants in their design, if they use DX system, they have calculated, for example, they use a heat load calculation, this is maybe 1 horsepower or 10,000 BTU, they will normally times 1.15 in their specifications to account this type of overrated capacity by the supplier. I think that is important, no? But consultants somehow also in their practice, their standard practice, if they use chill water system, for example, then they don't mark up. Because chill water systems, all the manufacturers, they have their standard software. They will select the cooling coils based on the software and also based on the actual on-coil conditions that designed by the consultant. But you will be confused, you know why? A lot of consultants, they don't design the heat load properly in the way that I have actually presented just now. If all the components come in and then how many CFM and then use the mixture formula and calculate what's the on-coil temperature. They just use BTU and then they give you total, they don't give you on-coil temperature. So if they don't give you on-coil temperature, there are many ways for the supplier actually to give you under-specified capacity. And this is very important for us actually to take notes when we handle a project. Almost 15%, very big capacity, very dangerous. No? But why, then you ask me, in the past, many jobs consultants, even though there was not a way of this these ratings, why a lot of buildings, the coolness was still no problem? Because in their heat load calculations, they already mark up so much already. That mark up already cover all this overrating already. That means they get away because of oversizing. If let's say if a consultant is so how to say aggressive, they design the heat load just ngam, for example, and selecting the standard rating of capacity from the catalog, surely actually will not provide enough cooling. Okay, just now I was talking about the DX system where you have the direct expansion, the refrigerants directly cooling the air core direct expansion system. So now A is cooling the condenser, it's called air cool. Air cool, this is called air cool already. Air cool system, okay? Because the air is used to cool or to extract the heat from the refrigerant circulating through the condenser coil. Air cool, So, but now if I change the component of this component, I change to this shell and tip evaporators. Okay, this shell and tip evaporators, that means it's a big how to say cylindrical shell inside submerged inside the with a lot of copper tube. Okay, like this. A lot of copper tube. So water is circulating through the tube, and the refrigerant is flooding the tube and circulating through the shell. So if I convert the structure of this one into this one, so these structures I'm going to use it to produce water, not cooling air anymore. Okay, so I'm going to produce water and then use a pump to pump the chill water to this coil, and then this system become chill water reader. Understand now? And the entire system here we call air cool chill water system. And because these refrigerant systems combined together become a air cool chiller. Okay, like this. The system I showed you just now is a big air cool chiller. Okay, air cool chiller is like a very standalone big outdoor. But this big outdoor condenser comes with the evaporator, shell and tip evaporator that can produce chill water. You can put outside. This chill water, we use a pump to circulate the chill waters through the piping, all these things, right? And distribute into fan coil, AHU, like this one, like this. So there are connectors there, you can see. Okay. So what is the standard temperature of chill water supply and return? Sufficiency is what? Is supply or return? Supply supply. And then return 12. Okay, it's about the under ASI standards is 6.7 degrees C supply chiller and return is 12.2 which is 44, 54. Try to memorize this one. You have to, because this is an ARI standard. And this is the temperature where we standardize it as an optimum temperature where it can, where it's applied to the AHU or fan coil, it can bring down, it can cool the air very effectively. At the same time, without burdening the compressor to work too hard. Meaning that, of course, if I can bring down this temperature, when I bring down this temperature, here the air can be cooled much faster, but compressor here actually is working harder. So I don't want, because compressor actually is the biggest component that consumes the most power in the chill water system, right? So I try and error already. Let's say in the past, a lot of laboratory tests have been carried out already. So this is the middle level temperature, where chiller running comfortably, not too hot, compressor not too hot. Air here is being cool, also very effective. Okay. So based on this, of course, I would like to share with you there are some standard formulas to calculate actually the chill water pump. Okay, the chill water pump, the flow rate here, of course, you see the US GPM equals to the capacity in terms of RT here times 24 divided by the delta T. The delta T here is 10. Wrong. What is the delta T? 10. Then which delta T 10? So which one minus which one? Yeah, this one minus this one, no? Yeah. Okay, so from here you can see 1 ton of cooling 1 ton of cooling correct not? Here is 1 correct not? Is equals to 2.4 US GPM. That means 1 ton of cooling you need 2.4 US GPM. Not equal, is equivalent 1 ton. If I increase the delta T here, what do you think the impact? US GPM impact, increase or decrease? US GPM increase, man? I increase the delta T. Delta T. Decrease. Okay. If let's say I use 56 for example, right now, I use 56 So here one ton I need to use lower 12 divided by 12 divided by 12 is 24 divided by 12 is 2 US GPM. Correct. So if I reduce the flow rate, what component that you think the first immediately benefit from it? I mean in terms of sizing if let's say you are the designer, pump, correct not? Pump size will reduce, right? Correct. Okay. Another thing, another component that you can see possibly reduce, piping, piping sizing, valve, right? Maybe then your pump motor also reduce, cable reduce, your starter reduce, control panel reduce. You see the impact, right? But don't be so happy, so complacent by this benefit yet. Okay, when you do this, all this reduce, right? Wow, very happy, But the chiller actually, the efficiency here when you increase this one, the chiller reduce one. Okay. But there are some way the chiller, they still do some redesign, okay, without so burdening, they can still tolerate with this increase without much impact. The supplier said, the factory said, okay, I can still massage a bit, okay, no increase in power, no increase in what, little bit of cost increase only, okay, and sell to you. You are still happy, okay? So then all this benefit here, okay, you still can enjoy it. But technically, whenever you increase this one, I can tell you that this one will be penalized. Whether actually the manufacturer want to pass this penalty to you or not, that will actually, how to say, change your decisions whether you want to go for this or not. If, as a manufacturer, I don't want to absorb these penalties into my cost. I pass it to you, okay, and your decision to enjoy all these benefits may not materialize. In Chinese, called lan pa pa lan. Sorry, understand? So, like I say, of course, when the system is increasing in size and the chiller plant room is further away from the system, a lot of long piping, yes, it's worth considering this higher delta T. Because the piping cost is very high when it's pipe is long. So all this saving almost quite certainly can be much more compensating the penalty that you face here. So is it good actually to learn new things like this? You see, when, of course, then you ask me, 42, also okay ma? 42, but I use 52 lah. 52, the delta T still the same ma. So what do you think? Will it affect the efficiency of the chiller or not? Delta T same more. Delta T same, flow rate same. I lower the temperature here only. This lower temperature, when go to the AHU, okay, before I ask you this question, why I want to design lower temperature? Then I go to this AHU here, the cooling coil is colder, right? Then I can design actually the lower air temperature coming out from the coil. When I do this, of course, I also can increase the air, the temperature difference. When I increase the temperature difference, the airflow, I also can design lower. When I design lower, your fan is smaller, fan motor smaller, duct smaller also. Very happy also, right? So, okay. So, but do you think actually this temperature is same delta T? No change in delta T, no change in flow? What do you think? Will we burden the compressor? Will. What do you think it will? Why? Yes, 2 more volt. 2 more volt. Correct. 2 more volt. Because when you need to produce colder chill water temperatures, your refrigerant temperature have to bring down lower. In order to bring down lower, you compress harder. So if harder, you consume more power. So all the saving that you think that some people may disguise it from you. You say, tell the owner, change everything's here showing a lot of saving technically. At the end, the monthly bill does not show the saving. Because why? When you combine with the chiller actually is offsetting already. It's have offset all the saving here already. That's it. Having said this, there are some suppliers, when they design the chillers, in certain ways, when they optimize the chiller combinations of this one, they still can actually achieve some saving in certain way. But theoretically, I want you all to understand the true fact first, and not to be carried away by all the we call it what, gimmicks. There are many people actually created these gimmicks to convince or so-called to impress a lot of, I would say, ignorance owners of adopting actually this one-sided strategy to believe that actually they can get a lot of saving. I try actually to create this better awareness among us that these one-sided savings not necessarily can be materialized if the balance optimizations have not been done on the center chiller system here. Okay. Okay. Shall we have a maybe 5 minutes break first? Or okay. Yeah.
So your lecture notes today, can you share later?
Can.
I need to go for something.
Nanti siapa tu saya sudah boleh.
Okay. It's very interesting. But I have to be so sorry.
Okay.
I would have stayed if no other things. But okay, I have done notification.
Oh, the food is here already. Yeah, the food is here already. Oh.还有很多东西要学Wong，这些这些只是一些很表面的。我现在
因为我看惯，我们用惯手机，我不了吧？
Hey, eat lah. Take by yourself lah. Then I have order. Oh, now the burger very small only, Last time the burger, I ordered 7 set and burger 7 set. And then nasi lemak also got. Okay, you take this, and then this is also the ice cream. Break 吗 ？Break 吗？我想5 minute break 吗？很快continue 了。OK， 你给他们了 ，OK 了。全部够了，咁样够了的，然后有 extra 一 set nasi lemak， 还有一 set 那个 porridge extra 的这个，7 set 是否他没有来，他要什么？给他了。 吃了，他们吃了哦，很小粒罢了哦，够力哦。哎，哎，滴滴滴，
银行还要证明他来的时候，他来的时候那个快递包。如果来到你的是有些是他快传送的，你就可以扣那个邮箱的，你的快传送还是没有过来。
Everyone also one burger. One burger, everyone. 好。然后每个人都有这个 ice cream， 还有多出来的那个粥是，你吃了？啊。
到了。汽水。快餐你不会去水就少一个零，基本我那个零和出现掉，所以我吃炸鸡哦，所以我就喝。所以讲那个气热，如果我们要做到很冷的，就要用那种温热气热。
对的。OK， 如果 temperature 是现在如果跌到大概36度的话，就用那些不能用水了，就要用开锅。
哦。
就是我们起热是我们的结冰的温度是32或是0度嘛，是吧？所以我们起热是通常了，以前是现在可能他们已经改变。以前我们是你的起热是可以 operate 是要有一个 buffer temperature， 大概是8到10度，就是说32你再加8的话是一定要最低可以让到40度咯，就是起热啊。你一让到比如说就是他们就不担保你了，他们就不 certify 你了，因为什么？因为有些起热是你的水啊，那个水一下子那个 flow 啊，一下子 fluctuate 啊。它会结冰的哦，因为它不够时间嘛。起热要大概8度的这个 buffer 啊，有足够时间去应付啊，你这样子嘛。所以
如果硬要的话，然后那个水加一些东西在里面。
开锅咯，
它就可以把那个
freezing point 哦，降低了，降低去。对。对。
它还是stay 在 liquid form 啊。
对。所以你的开锅越浓的话是就可以降就越低咯。所以那些 food 的 industry 做 chocolate 那些是，他们起的是 run -25 degree C 的，所以那些开锅加到大概50% 这样的，明白啊？合理的。
-25。
对，-25。然后它的那些开锅啊，是你要用那些是不是有毒性那种啊？要那种叫做 propylene 开锅是人啊吃到身体还是不会伤害的，有一种是ethylene开锅是伤害身体的。所以那 food industry 也是要注意的，我们不可以乱去 propose 这样子。所以那个谁啊，那个 Vertical 那个 Greenfield 那个家伙 那个 Lim 啊，他对 food industry 很熟嘛。他是熟是什么？是啊，他是 process 白冰，我们是熟什么？是 chiller system。如果我跟他合作起来的话，是我可以，大家都可以。
那就是直接加在白冰里面。
对对，加在白冰里面的。
没有东西，其乐那边不能做哦。
嗯。
是这样啊。
其乐。苦力块是另外水。
好像我讲的是有时候结冰，结冰了过后是嘛，然后呢过后有一块块很薄。
你知道为什么吗？它是这样子的，有些时候是你的 gas 不够的时候哦，不够的时候是它的那个 pressure 里面的那个 cooling coil pressure 就一下子降得很低，降得很低的时候是，但是你知道我们 coil 都一直有 condense 那些水分出来的嘛，就变成它不是把它那个水啊结冰了哦，它结的时候是薄，越结厚咯，厚到时候是塞住的时候是你的那个 air coil 就明白吧？就这样哦。啊？top up gas 啊。
整个车嘛，是加进去，整个车那个结冰，不够干。
是那白冰问题哦。有洞啊！我跟你讲啊，有些时候啊，我们一天也是面对问题啊，可能到现在啊，有些我就是一直给他气死我，因为他埋的那个白冰在窝里面呢，又拉不出来哦。但是呢，里面肯定是有那种 fine leak 啊，它又不是一下子 leak 出来，它点啊，它跑了半年到8个月哦，它开始才不冷。
所以每半年8个月你就要。
是。
Wedding attending. Maybe a wedding. I have to go to Rawang because they have 11 to 3. So I have to. Bye.
A lot of good thing to learn here, bro.
Huh?
A lot of good thing about chiller nanti.
Yes.
Yes.
That's why I say I asked.
If you want to sell chiller later, all this must be able to capture.
And the basic things.
Yeah.
To understand.
还有很多东西写的。是啊。不过我平常很少，我平常不吃的这些，真是没有吃的平常，几个月吃一次可能有了因为我I'm not fancy this kind of thing。
还有一个粥。还有粥。
还有酒可以吃啊。
拜拜。
那些 ice cream 全部都每一个人都有份啊。我不吃了，因为就好像你讲太甜了，太甜了。美多那的粥不错的，OK 的。
前几天才吃来吧。
明天去吃它32块，32分钟的炸鸡，unlimited。
什么32分钟
？32块。
32分钟。
32分钟，你吃它炸鸡unlimited。
你去吃啊？
对吧？
这样比较便宜。
不是没摇的呢。
32分钟
里面
你要吃多少炸鸡？对。能吃多少个哦？吃几个就饱了哦。吃3个都饱啊。可以打包吗？肯定不给你打包啊。这样讲，如果云顶着 aircon， 它的 ambient temperature 就低嘛。
所以它的chiller是 可以省很多了。
它的路很小啊。
小的。然后这云顶是这样的，它呢，哦，我刚才讲了什么？
处理。
look at tree 啊。
哦。
它上面给你插，啊，Type C 的，Type C 的，
这个。
哦，
老板，你电话没有电了，老板。电话没有电了。
这个是什么的？
这否那个麦的。
那买的。
不够电了。
不够电了。没有，还是你 charge 这个还会 charge？
这个只是 charge 这个吧？
它不会 charge。
这有 Type C 的，是有 Type C 的，接一下。
那边有，好像我看到很多土地。
这样就不用用这个，看一下可以声音听得到吗？
听得到。
你在你在那边讲话这样。
testing 啊。
听到吗？我讲大声一点哦。你现在我是想跟自己用不同的方法去讲话。哦。你知道吗？好像他们中国人讲话要解释一下吗？